go ahead and start recording. Data structures, teaching. Exam 2, practice. Okay. So as usual, so here this only added up to 103 points. That's okay. On the exam it will be 105. Okay. So the first page will be something like this. There will also be a page like this on the final exam because I'm writing the final exam. So I get to put in and say, hey, there's going to be a page like this. So for each of the following questions, indicate which data structure will be best suited to handle each scenario. Your choices are array list, linked list, stack queue, tree, priority queue, set, or map. Also, one thing that I've noted from people messing up this question over the various years, recursion is not a data structure. Okay? Recursion is a programming technique. If you feel like you need to use recursion for something, then what data structure does recursion use? Stack. Recursion uses a stack to backtrack and stuff. So let's go ahead and see. Let's go ahead and get through this. Let's go ahead. Sorry, 1 second. Yeah, come on. All right. You need to model which patient should be seen next at a hospital. Patients should be seen in as close to the order of arrival, but patients, whoops, close. Okay. Sorry. But patients with a more severe situation should be seen soon, be seen first. What data structure is this? Priority queue, right? This is exactly what a priority queue is used for. People get to cut in line in priority queues. A router needs to hold packets in a buffer and deal with them in the order that they appear. That is a queue. Right, you deal with a buffer, that's basically the solid use case for a queue. Besides like trying to limit people getting into a resource, a router using a buffer or something using a buffer saying, hey, I'm going to deal with data in the order it appears, right? First come, first serve, right? That's a queue. We need to model a hierarchy of some kind. That is a tree. Trees are the hierarchical data structure, right? Anytime there's a hierarchy or a taxonomy or something like that, where basically that there's branching out from something, that's a tree. Notice that over here it does say tree as opposed to binary search tree, right? You need a data structure to hold your previous decisions in case you need to backtrack. So that's a stack. Backtracking is using a stack, right? First in, last out on the stack. So, sorry, and I'm just going to go ahead and create a new file over here for when we need it. New class. Yeah, new, oh, come on. New, you're just not liking me doing new, really? All right, we'll just go into here. Why isn't it able to create a new Java class? Thought I was working in Java. Seriously? What is going on here? Yeah, whatever. Just new, I'll create a new project from this then, and just simply do that this way. New project, 10, next, exam review. Okay, this window. Okay, and then there's our source file folder, new Java class, review. Okay. All right. So answer the following vocabulary questions. The node at the top of the tree is called what? Not the parent. What is like the parent? What is the parent of everything? It's called the root. So if we've got links from a node to its successors, what are those called? Edges. I'd accept that answer. Technically, not what I was looking for, but honestly, this is one of those things where you can accept it. I would the answer that is branches, but I will also accept edges, and actually, I'll accept links. The links from a node to its successor are called links. So this is one of those things where basically there is a very fluid vocabulary for trees. Anything that makes sense works here. The predecessor of a node in a tree is called what? Ancestor, predecessor, parent. All those work. The predecessor of a node in the tree that specifically is the parent. Its predecessor, which is a more specific term for the predecessor, and that is a specific type of ancestor. Ancestor is all of that. Nodes that have the same parent are what? Siblings, yes. There was really not a formal term for it, so we just borrow from the family tree terms. Sibling. So describe without using code how to calculate the height of a tree recursively. Let's think about that for a second. What is the definition of a height of a tree? Right? What is the height of this tree over here? Let's see. Over here. What is the height of this tree? 4, right? It has 4 levels. The height of a tree formally is the distance from the largest distance from a leaf to the root plus 1. That's formally what it is, right? So the height of if it was just this, the root, be 1, right? If we didn't have a right side, it'd be 2, right? Because the distance to the lowest leaf plus 1 would be 2. Also, it's how many levels. So how could we calculate this recursively? Right? Any ideas as to how to figure out what the height of the tree is recursively? Let's go ahead and generalize this, shall we? Right? When we try to calculate stuff about trees recursively or figure stuff out about trees, we shouldn't really think about the actual tree. We should think about the node we're currently at, right? Which may or may not be the root of the tree, and then it has a left side and a right side, which are mysteries to us. They could be null, they could be ginormous, right? So how can I figure out the height of this tree recursively? Yes?
You get the height of the left and right, pick the biggest one?
Yeah, figure out which one of these guys. I'm going to ask, so to get the height of my tree, I get the height of my left, get the height of my right, ask which is bigger. Which one is bigger? Let's go ahead and say the height of this guy is 5, and the height of this guy is 2, right? Obviously, this guy is bigger, right? So then my height would be what? If my left side is 5, mine is 6. It's 1 more than the bigger of my. So I'll return 6, and that might be the answer, or I might just be returning that to my parent, right? To let them know what my height is. Right? So recursively, what I do is I look at my left subtree and my right subtree, ask what their height is, and let's see, and then I get the bigger of them, and then I add 1 to them. Now, then the other question we have to ask ourselves is, okay, that's the recursive case. What about the base case? What if the base case is for our trees is almost always this, right? Nothing. So what do we do if we have nothing? What's the height of this tree over here? 0. So we return 0 if it's empty, right? Height of this tree is 0. So if this side is null, we'll just return 0, right? So if this guy ends up being a leaf, right, his left subtree will return 0, his right subtree will return 0, and he'll return 1 himself because it will be 0 plus 1, which is a valid answer, right? In case you're wondering, by the way, like you might be going, if statements are terrible to write to figure out how big something is. The math function the math library is actually full of nice, useful little functions. So if you have to code this up, hint, hint, nudge, nudge. Then there's a math.max function built into Java, which given two integers will return the bigger of the two integers. So that skips the whole need for making an if statement to tell which one is bigger, right? And what if you have, so the question, of course, is not that you're going to run into this. Well, what if I have three things that I need to figure out what the max is? Well, that's fairly simple. The max of A, B, C is equal to the max of A and the max of B and C, right? So if I need to figure out what the max of 3, 4, 5 is, I can just simply do this. Math.max 4 and 5, right? I can nest that with as many math.maxes as I need, and it will all work out. Okay. All right, so let's go ahead and draw an example of each of the following types of binary trees. Use a different example for each possible tree. Now, the reason I mentioned this, because we're drawing a full, perfect, and complete here, is because because if I didn't put that clause here, you were well within your rights to put this as all three answers. This, because it is full. What does full? How come it's full? All the nodes have no children or two children, right? It's perfect, meaning that basically it has a height of h, and it has 2 to the h minus 1 nodes in it. Okay, which is just basically the mathematical definition to say it's pretty looking. It's nice and symmetrical. And then it's also complete, where basically it's perfect for the top, for the uppermost levels, and then the bottommost level, if it has nodes, it's filled from left to right. Okay, so let's go ahead and just draw some examples of a full tree. This is full. And let me go ahead and switch this over so that I can actually see, so you can see the screen a bit better. Okay. This is full. This is not full. This is full, right? Every node has either 2 children or no children. Okay. If I draw 2 more nodes over here, it's still full because every node has either 2 children or no children. Okay. Everything is either a leaf, or if it's not a leaf, it has 2 kids. Right? Okay. So the other one is complete. This is not a complete tree, even though this area is perfect. Let's first just talk about a perfect tree, right? This is a perfect tree over here, if I draw it like this, right? Everybody kind of knows what a perfect tree looks like. It looks fantastic. It looks symmetrical. Everything is filled up. The bottom row is all even with each other because all the leaves are on the same level. There's 2 to the h minus, this has a height of 3. It has 2 to the h minus 1. So 2 to the third minus 1 nodes in it. It's got 7 nodes in it. That's what perfect means. It's all of a certain height, and it's got this many nodes. Basically, we're saying for a tree of height h that all the spots that are possible are filled up. Okay? So for a complete tree, it's saying it's perfect for this level over here. It's perfect for h minus 1. But for the bottom level, it needs to be filled up from the left to the right, right? And we use this primarily for heaps, right? We don't want a gap in our heap because we're going to be translating that as an array, and we don't want any gaps in our array. So here, right, this is perfect. Sorry, this is not perfect, but it is complete. It's perfect for this area, but left to right, it's complete, right? So notice we've got a child here, a child here. If we put another child here, still complete. But if I put one over here, now we've got a gap going from the left to the right. And therefore, it's not complete. Does that make sense to everybody? Now, one question I will not ask you to on the exam, okay, although I have been tempted, very tempted in the past, but I think it's cruel and unusual. And last I checked, you have Bill of Rights constitutional protections against cruel and unusual punishments. So I will not be asking you to write a method on the exam that asks you to, given a tree, tell me whether or not it's complete. That seems rather terrible. Because I'm not sure how we go about that particularly. So I don't ask you to do. I generally don't ask you to do something I don't know how to do. Generally. All right. So, so let's go ahead and now get into the bulk of some of our questions, which is binary tree operations. So this will be worth a certain number of points. This question will be exactly the same as on the exam, maybe worth more points on the exam. Again, the only difference is the numbers that you will be adding to the tree, right? Make sense? The only difference is the numbers that get added, right? You don't have to do it step by step. You can just simply like add everything. But you know, if you mess up, of course. And people do mess up on this, but not like for a huge amount. It's very rare that somebody misses more than 1 point on this. And that's if like you have no understanding of how it works. If you like, oh, I thought that I missed the negative sign for the 12 over there, right? Or I accidentally transposed the negative in front of the 8. Whatever. You know, the point is, do you understand how things are added to the tree? Not are you exceedingly perfect under stressful situations, right? Because you're not. You're human. I want you to be solving the. Nobody, you know, you're never going to have to deal with a life-saving situation where you have to, you know, add nodes to a binary search tree. So, don't need to really rely on perfection there. Okay. So the first thing we do is we add 42. So that becomes the root of our tree. Now this is a binary search tree, but it's not a self-balancing binary search tree. So we're just going to add nodes to it. So next is 10. And let me go ahead and switch the camera again. So 10 to the left, because it's less than 42. 50 to the right, because it is greater than 42. So we go 50 is greater than 42, so we go to the right. Next is 12. 12 is less than 42, greater than 10. Go to the right over here. 17, less than 42, greater than 10. Greater than 12, so 17 goes over here. And again, it doesn't have to be like perfectly drawn or anything, just the connections have to be correct, right? 80 is next. So 80 is greater than 42. It's greater than 50, so it goes to the right over here. Negative 12 is less than 42, and it is less than 10. Remember the way negative numbers work, right? So it can throw you off in the middle of an exam. It sounds silly, but you know, it just happens, right? Where basically you just have a brain fart, so to speak, right? And go, 12, that's negative 12, that's bigger than 12 is bigger than 10, right? Totally see how somebody could do that. 100 is greater than 42, 50, and 80, so it goes to the right over here. But now 96 is greater than 42, 50, 80, so we get over to 100. So we go, right, 96 won't go here. 96 is greater than 80, so 96 goes over here. And we go ask 96 versus 100. 96 is less than 100, so it goes over here. 105 is bigger than everything else, so it goes all the way over here. And then 86 is, let's see, 86, greater than this, greater than this, greater than this, less than this, so 86 goes over here. 72 is greater than this, less than 80, so 72 goes over here. So this is the correct answer for this problem, I believe, assuming I haven't made any mistakes. Right, but the point being is that all we do is that we just simply ask, for the number are we at? Are we bigger? Or are we bigger? If so, go to the right. If we're less than, go to the left. If it's equal to, you aren't going to get an equal to. So don't worry about that. But in general, for when it comes to equal to, you got to have some rule. And your rule can either be either be having no duplicates because I'm building something like a set or a map, or I can just have or I can say anything that's less than is equal to. Sorry, anything that's equal to is less than. Okay, so now the next questions. Using your previous answer, draw what happens when you remove the following. So first we are going to remove 42. So there's 3 cases for when we remove items, right? Which is that we are removing items we're removing an item such as 17 or negative 12, which is a leaf. So we can just simply remove them, blot them out. Next is we can remove something like positive 12, which has one child, in which case 10 would adopt 17, right? And then finally, we're in the case where we're moving something with two children, where it needs to be replaced with its next in-order predecessor, the biggest thing that is smallest than it. Now, on the exam, again, you could give me a full answer, but I highly suggest that basically you just show me what happens after you remove one item at a time. And on the exam, I'll also give you, I won't be making you work off your previous answer. Instead, I'll actually give you a tree and tell you to remove items from it. Okay, so the first thing we got to do is remove 42. So the first thing we have to do that is find the biggest item that's smallest than it, biggest item that's smaller than it, which is our next in order predecessor, which is 17. How do I know that? You find your next in order predecessor always by going one to the left and then going all the way to the right. One to the left, all the way to the right to find your because remember, this subtree over here contains all the items that are smaller than 42. All the items that are smaller than 42. So it stands to reason that the biggest thing is going to be the thing that's all the way to the right on there. And yes, if you use the smallest thing, you could technically use 50 as well, which is the smallest thing that's bigger than me. But I want to do it this way. Okay? So we copy over 17 over here, and then we delete our original 17. Okay? So we copy over 17 over here, then we're going to delete our original 17. How do we do that? We will erase, well, we're deleting 17. It has no children. It's super easy to delete, so we just remove it. So we just copy over that value and delete the original. Now let's go ahead and delete 12. 12 has no children now, so it's super easy to delete. Let's delete 17 now. 17 has two children, so we find the biggest thing that is smaller than it. Okay? What is the biggest thing that is smaller than it? Go one to the left, all the way to the right. And you can't go anywhere to the right, so the biggest thing that's smaller than it is 10. So we copy 10 over it into here, into our root, and we delete the original 10. Now deleting 10 over here means that we have one child, which is annoying, but we can still do that. When we have one child, we have our parent adopt our child. So what we do is that we just remove 10 and have our root adopt negative 12. Yes?
Could you put 50 there instead of 10?
I could have done 50 as well, yes. And then deleted 50. And then removing 96. Right? First we have to find 96. 96 is greater than 10, 50, 80, 100, 96, found 96. So we want to replace it with just its. So actually we don't need to really replace it because it's only got one child. So we just remove it and have its parent adopt its child. So have 100 adopt 86. All right. Next question. Which of the following is a preorder traversal of a binary tree? Okay. Which of the following is a preorder traversal? Any takers? B? B is not actually preorder. A is in order. In order traversal, right? In order traversal is you go to the left, you process, then you handle yourself, then you go to the right. All the things that are less than me, then myself, all the things greater than me. That gets you in order. Preorder, what is preorder? I handle, B was, sorry, my bad, B. B, it is B. Sorry. I was, for some reason, getting preorder and postorder confused. So B, process the root node, handle myself first, then handle my left tree, and then my right subtree. Okay? So it was B. Okay? So let's go ahead and take a look at a preorder traversal of this subtree. This tree, okay? So this tree is, so this tree, starts at 10. So preorder traversal says handle myself, 10, handle my left subtree, then handle my right subtree. Let's go to my left subtree. My left subtree is negative 12. No problem. So I'll just handle negative 12. Okay. Next on the list is we handle my right subtree. My right subtree is this entire thing. So we process our right subtree. Our right subtree starts with 50. So we handle 50, then we handle 50's left subtree, which is null, and handle the 50's right subtree. So then we're at 80. We handle 80's left subtree, and then we handle 80's right subtree. 80's left subtree is 72, and then it's got nothing else. 80's right subtree is this. It starts with 100. Then we handle 100's left subtree and 100's right subtree. 86, 105. There we go. So that is the pre-order and post-order traversal for this. Yes?
And you said A is in order.
A is in order. So what is the post-order then? Which of these is post-order? C. Handle the left subtree, right subtree first, then handle myself. So the post-order configuration is as follows. So first, handle my left subtree, then handle my right subtree, then handle 10. Okay? So first, let's handle the left subtree, which is going to be negative 12. Okay? Now I'll handle my right subtree. Then we're at 50. 50 says I'm going to handle my left subtree, which is nothing. Handle my right subtree, and then I'll handle 50. 80 says handle my left subtree, which is 72. Handle my right subtree, which is 100. 100 says handle my left subtree, which is 86. 100 then says handle my right subtree, which is 105. Then I'll handle myself, which is 100. 80 goes, I've handled my left subtree, 72, my right subtree, which contained 100. So I'm good to go. Write down 80. 50, handle set. 50 says I handle my left subtree, I handle my right subtree, so I can write down myself. And then 10 goes, I've handled my left subtree, and I've handled my entire right subtree, so I can write down myself. Let's keep going. I want to make sure we have plenty of time. All right, another question where basically you're just going to deal with the, another question where you're just going to be writing what's going to be, or drawing what's going to be going on, exactly as, it's the exact same question as will be on the exam. The only difference is that I will be giving you different numbers. So let's get to it. So remember, heaps don't work like binary trees. So you can draw the heap. You don't have to worry about the underlying array, right? You don't have to give me the array. I just want you to draw. You can give me the array if you want to. But I'm looking for the underlying heap. So first thing we do when we add an item to the heap is that we just add heap. The rule for a minimum heap is that the smallest item must always be at the root of a heap, and this is true recursively. So 8 goes in. Then we put 10 in at the next location that would make it complete, right? So we go like level 1, then right to left on level 2, then left to right on level 2, then left to right on level 3, and then left to right on level 4. Okay, so 8, 10, 50 is next, right? 8 is still the smallest. Then we do 20. Nothing too exciting there yet. And then we put down 1. 1 is definitely smaller than 10. Last I checked. So what we do is that once we get a violation, so we add an item, right, to this last location, and once we get a violation of the heap property, we solve it by swapping, right? We have the smallest item bubble up, while the heavier items, they sink down. So 1 and 10 will swap because 1 is lighter than 10 and 10 is heavier than 1, and 1 and 8 will swap, right? Because 8 is heavier than 10. Sorry, 8 is heavier than 1. So 1 goes all, so it swapped with 10 and then it swapped with 8. Now we insert 4. 4 is heavier than 50. Sorry, 4 is lighter than 50, so we swap it with 50. 50 sinks down. 4 goes up. And now we put in 3. Oh, and we stop over here. Why? Why did I stop? Yep, 4 is greater than 1. It can't go up any further. Next, we put in 3. 3 is less than 4, so it swaps with 4. And then 3 is greater than 1, so we stop. Okay. Using the heap above, draw the heap after removing an element twice. So we got to remove 2 items from this heap. So we always will remove the first item from our heap. So we're going to remove 1. And the way removal works is that you always remove the root. And let me just also specify what I look for to make sure that it's correct for the heap, so in terms of grading. I look for it being a complete tree. If I see something like this, where I see something like this, then I'll just mark you wrong because that's not a complete tree. Basically, if it looks like a binary search tree, then it's going to be wrong. So let's go ahead and work on removing this guy. So let me go ahead and redraw it. 1, I think I had 1, 8, then 3, and then there was a 4 here, a 50, 10, and 4, 50, 10, and then 20, right? Okay. Yeah, so let's go ahead and, so we need to remove 4. The way we remove something, so we need to remove 1. The way we remove something is we replace it with the lastmost item, which is 4, right? It was at the last position in this, left, if you're going left to right through the levels. So 4 goes up there, but now we're violating the heap property, right? So now what do we have to do? We have to let 4 sink down to its appropriate place. So we compare 4 to its children. Is 4 less than either 8 or 3? Yes, it is. So we swap 4 with 3 because it's less than 3. We put 4 where 3 was, and we swap 3 up. Now we look at 4 again because we're still sinking 4. How does 4 compare to its children? Well, it only has 1 child. How does it compare to 50? It's less than 50, so it can't sink any further. Now we are doing our second remove, which means we're removing 3. To remove 3, we take 50 and put it up here. Now 50 needs to sink down, but it happens to be smaller than both its children. Bigger than both its children. Both of its children happen to be smaller than it. So what do we do here? We need to swap it with its smallest child, because if we swap it with its smallest child, that means that the smaller child will go up to the root. So we swap it with 4. 4 goes up over here. 50 goes over here. It's a fairly straightforward process. Huffman coding. Consider a document that has the following symbols. A, P, L, E, X. Draw the Huffman tree for these symbols. And I do try to make the math fairly easy like that. Right? So, again, this will be not only on this exam, but also on the final exam. So, A, P, let's see, what was it? So it's E has the most, X has the least, A, P, L. Okay, and what are their weights? 1, 10, 20, 1, 20, 40, 50, 60, right? Okay. So, draw the Huffman trees for these symbols. So the way we do this is, remember, this is a priority queue. So we dequeue twice. We dequeue X and L. We add them into a node. X and L, which has a weight of 21. So you put XL back into the queue, 21. And we find that this weight is actually lower than everything else, so it goes to the front of the queue. Okay. So next we dequeue the next two items, which are XL and P. So XL came out first, so it goes on the left, and P goes on the right. And that will have a combined weight of 61. XLP, 61. Okay? And that will stay on the back because, guess what? It's heavier than everything else. Then we have 50 and 60, which will be A and E, which will have a combined weight of, 50 and 60, which will have a combined weight of 110. A and E, 110. So AE, combined weight of 110. And then XLP and AE are the remaining two. So we dequeue them, and we combine them into one node. Right? And it doesn't matter what their combined weight is at that point. So to create our Huffman encode, you don't need to put in the ones and zeros for this part. That's for the next part. Now, if you get this part horribly wrong, I'm going to mark this part wrong, but so long as your answer makes sense with this answer, you'll get credit for this. Right? So you don't have to get this first part right to get the second part right, as long as it's consistent with your answer. But generally what I do is I end up checking, okay, do you have the same do you have the encoding that I'm looking for? If you do, I can just glance at the tree and just grade it very quickly if it's correct. So I like that. So encode this string apple into binary. So we do the left sides zeros and the right sides of 1. So to encode apple, we need an A first. So A is 1, 0. P's are 0, 1s. 0, 1, 0, 1. L, 0, 0, 1. And then E, 1, 1. So that will give you apple. Okay. I think this finally lets us get to the nice and interesting part of our exam, which is the coding part. All right. So write a method for which, given the root of a tree or subtree, computes and returns the number of nodes in the tree. So can't use the size method, it says. So let's go ahead and I'm just going to make a quick private class over here so that I won't get a bunch of errors. Private static class. You don't need this in your code because I'm giving you nodes. You can assume they exist. But here I'm just going to say private static class node E, which will have a private date. You'll have a private E item, private node E left, private node E right. And this is just simply so that we're all on the same page here, right? And now let's go ahead and yeah, just do a constructor. No, I don't think I'll need it. Public node E item. This dot item is equal to item. So we don't really need that, but but just in case we do, I don't think I'm doing anything here that's going to create new nodes anywhere. So let's go ahead and just take a look. Write a method which, given the root of a tree or subtree, computes and returns the number of nodes in the tree or subtree. Okay. And we cannot use the size method. Sounds good to me. All right. So this is all the. So every single piece of programming that you're going to be doing for. Every single piece of programming you're going to be doing for trees is going to be using recursion. This is nice because that means I don't have to ask you any extra recursion questions, right? Furthermore, they're always going to pretty much use some variation of the traversal algorithm rather than going left, choosing to go left or right. So you know basically that you're going to be basically hitting every single node in the tree somehow. Okay, so first off, let's just go with our base case, right? This is the way we solve these things. First off, always figure out the base case. Base case is always worth a couple points, even if you can't get anything else. So first, what is the base case? Like, how would we know if we're in a base case? Yep, if root is equal to null, and the thing I'm looking at is empty. So in that case, if the root is null, what is the size of the tree? 0. If I don't have an item there, then its size is 0. Okay. Otherwise, let's draw how big this tree is. Okay. Otherwise, again, let's draw our hypothetical in the middle of a computation tree or subtree, right? Which means drawing. This is root. This is my left subtree. This is my right subtree. So what is the size of this in terms of recursion? What is the size of this?
Plus right plus 1.
Yep, it's the left side plus the right side. The size of the left side, size of the right side, added together plus 1, right? So I need to figure out how big my left side is, how big my right side is, and then add 1 to that. So let's go ahead and write that. Okay, int left size is equal to size of tree root dot left. Okay, because again, figuring out how big a tree is, that's a hard problem unless I'm at the base case. So I'm just going to call it recursively, right? The left size is equal to the size of the left tree, okay? And then the right size is equal to right size tree root dot right, and then and then basically the size of me, I guess. I'll go ahead and create a. I'm going to show you the quick way to do this, and then I'm going to show you how. Sorry, I'm going to show you basically the thought process way, and then I'll show you the condensed way. Middle is equal to 1, right? Myself is equal to 1. Okay, and then I'm going to return the sum of all those things. So left size plus right size plus middle. Or I could do 1 there. Right? However, I can actually do this I can actually do all of this in one line, in a fairly straightforward manner, because there's no decision-making process over here, which is that I can just simply say return size tree root dot left plus size tree root dot right plus 1, right? Now, let's think about how this works. Why does this work? Well, if I've got items in my left subtree, it will call this algorithm again and figure out how big that is. If I don't have a left subtree, guess what? I'll get 0 back pretty instantly. Same with my right subtree. We'll figure out how big it is. And if my right subtree has as one of its left or right subtrees as a 0, it will get 0 back and then get the size of its other tree, and so on and so forth. And then it will pass that all up the way, because everybody who's a node will count themselves with that plus 1. Any questions on that? Okay. So let's go ahead with this one. This one's a bit different, and I like it because it's different. Write a method which, given a tree, returns whether the tree is a full tree. So let's think about that. So let's think about that. We need kind of to figure out our. This is different because we actually have to do a bit more cases over here, right? So we have to figure out our base cases first. So first, let's just start off with our standard base cases. All right, public static e Boolean is full node e root. Right. So we're asking, is this tree a full subtree or not? Okay. So first off, I don't know. So let's go ahead and just go if. Let's start out with our standard if root equals null. Now I don't actually know what to do here. So for right now, I'll just put return false. Okay, I can always go back and change that later, right? I'm going to assume if there's nothing there, then maybe I'll just return false. But I might not actually call this. I might actually get rid of this. And I'm going to put a return false over here as well, just as a default case, so that I'm going to stop getting compiler error. Okay, but let's think about what it means to be a full tree. Yes. Oh, I call it tree. Yeah, sorry. I call it tree, but I'll call it root here. That's fine. So a full tree has either, if it's full, it will have a left subchild, a right subchild, and a right subchild. So a left subtree and a right subtree. Or it will have no children. So that actually seems like it's fairly easy to check some of those cases, right? So let's just go through this then and check those cases. If root.left equals null and root.right equals null, then at least we know that this subtree or tree would be full, because if I don't have a child on my left or my right, then guess what? I'm by definition a full tree or subtree. Return true. Similarly, I know if root.left is null and root.right is not equal to null, right? In other words, if I have a left subtree, right? But I have it, that's why it's not lined up. If I have a left subtree, but, if I don't have a left subtree, if I don't have a left child, but I have a right child, okay, so I have a right child but not a left, that means that I am not full. I have only one child. So return false. Similarly, if root.left is not equal to null, in other words, I have a left child but not a right, root.right is equal to null. So I have a left child but not a right. That's also a false. Okay? So it's working out differently. I have a feeling with all these left and right checks that I'm doing, I don't actually need this one. Right? I don't actually need this upper check over here, because I'm not ever going to call it. I'm never actually going to call it on something null. Right? So my only other case over here, right? I have two children, so there's four possible combinations, right? Have none, have left, have right, have both. So now here, if I have both children, that means that myself might be full, right? I have two children, but I don't know about my children, right? So in this case, I have to figure that out. Else, I need to get my, let's go ahead and say Boolean left full. Okay, and I'll just leave that there. Boolean right full. Okay, so I'm going to figure out if my left subtree is full and my right subtree is full, right? Because I know myself, I have two children. But since I have a left child, he might not be full, and my right child might not be full. If only I have a method that could check if something was full. Turns out I'm writing it right now, so that seems like the perfect use case. So to figure out if my left subtree is full, I will just simply say is full root.left, right? And I know that root.left isn't going to be null because by definition, because of the checks we've done, if it was null, we would have stopped somewhere. Same with my right. Okay, so I've got my left and I've got my right. And now what I can do is I can return it left full and right full as my answer. So what I do is I ask, is my left, okay, I know I have two children. So let me ask my left subtree, and it will check if any of the nodes it has in its left side violates the property. Okay? Do any of the nodes in the left side violate the full property? Do any nodes in the right side violate the full property? Right? And it will recursively call that, right? It won't need to call its children unless it has both children, right? If it has one child, great, I can just stop looking. If I have no children, I also stop looking because I have nothing to look at.
That can also be done in one line.
Yep, that can also be done in one line as well, that else statement. But yes?
So the last statement is like a boolean for every subtree?
Yes. So check my left subtree and ask if it's full. Check my right subtree and ask if it's full. Let's go ahead and take a look at how it works, right? Right. So if I've got a case like this, that's fairly obvious. I'm just going to return true to my parent because this side of the subtree is full. If, on the other hand, I get in a situation like this or the flip, then I'm going to return false because guess what? I violated that, and that will pass a false back up to its parent because of the and. Otherwise, I'm in a situation like this. Right? And I'll go ahead and remove this and say, we won't focus on this side. We'll just assume that it's there. But over here, right? Well, the way this will work is that it will check its left subtree and ask, is my left subtree full? And we'll get back true or false. Here, the right subtree will check it on the right subtree. Now this node will go, okay, do I have a left sub? Are both my children null? No. Are both my children, is one of my children null? No. Okay, so I'm going to check if my left subtree is full and if my right subtree is full. We'll go into my left. This guy will say, do I have no children? Yes, return true. So this guy will return true. Same with this guy. This guy will also return true. So we'll get this over here. These are both true. And I'll return the value of true and true. So I'll return true up to here, which will return whatever he got on the left and whatever he got on the right. Let's go ahead and see what happens, though, if we've got something over here like this, okay, where it's not full. Okay, so we'll get whatever. So over here, right? Do I have a left sub? Do I have one? Do I have 0 or 1 children? No. Otherwise, I'll get whatever the answer for my left is. Right? I'm just going to leave that as a big question mark right now. It doesn't matter for the purposes of our example and running through the code. Okay. My right subtree, I'll ask. Okay. Okay. So now we're at this node. Okay. We're looking at this subtree. Do I have no children? No. Do I have 1 child? No. Okay, so I'm in the else statement. So I first need to ask if my left subtree violates the property and my right subtree. Let's ask my left. My left says I have no children, so I'm going to return true. Okay? So now I'm going to ask my right subtree. My right subtree goes, okay, do I have no children? No. Do I have is my left side null, but my right side has something? No. Do I have something on my left, but nothing on my right? That does seem to be the case. So this guy over here, without even having to call this guy yet, will return false, which I'll just do with an X over there. And then this guy will return false as the is right. And so then I'm going to return left full and false, which will be false no matter what. Right? So that's the way that works out. So sometimes when you have a combination, sometimes you'll need to go through multiple if statements for these questions, but, and this is a big but, there will never be more than 4 combinations in any of the examples I'll show. Yeah. Is that a question?
No.
Okay. All right, so let's look at, and I do like, again, asking for properties of trees. All right, so this is another one of those cases where we'll get 4. This used to be my practice problem until I came up with the is full one. I thought this one was better. The is full was much better because it's something you can concretely, it's interesting and it's different. So write a method which, given 2 trees or subtrees, returns whether or not the contents of the entire tree are identical. In other words, do they have both the same data in the exact same way? So not only is the data the same, but we have to ask ourselves, do they also have the same structure? Okay. So this is one of those other tricky ones over here because this is one of those other tricky ones over here, and I'm just going to say return false because we've never really compared 2 trees at the same time before. Okay. So again, we just kind of got to ask ourselves our base case about our base cases here, right? And let's go ahead and draw that, right? If you haven't figured it out, your best weapon for coding is pencil and paper. That's part of the reason why I have you do exams on pencil and paper, just simply so you can get used to the process of drawing things out and relying on drawing things. It's also because it's much easier to grade pencil and paper, but I'm trying to transition away from that, so, and various things, so we'll see what happens. Okay, so, one other thing is that when I have a much larger class, it's very hard for me to check everybody's screens at once to make sure nobody's looking up something on the internet or using something or copying a file that they already have, right? So electronics make things complicated, you know. It is not true story. It is not outside the realms of possibilities that you just hire some guy on Fiverr or something to complete your exam for you while you're working on it. I mean, and you think that in jest, but there was a pretty prominent case of a guy who was working for a coder who was working for an American company, and all he did was basically he subhired somebody else, paid him a third of his salary, and then slacked off by reading Reddit all day. So he just simply paid somebody else to do his job, somebody who was living in India or China where the cost of living was much, much, lower, and, that was rather a lot of money, And yeah, he was paying a lot of money to do that, but oh my, he got to spend his day looking at cat videos and, and before you go and thinking that this is a great idea, he got fired because that was a huge security risk, All right, so let's go through the base cases of equals, okay? A and B. So let's draw our various possibilities. A and B. So tree A. So possibility 1, tree A is blank. Tree B is blank. They're null. Are they equal? Yeah, I'd say so. Yeah. If these 2 subtrees are equal, then great. So, right, we're going to just, and again, with these kind of things, we just want to figure out, we want to be lazy as possible, so we go through our easiest possible solutions first. If tree A is null, and, yeah, I will admit, basically, to that scenario I just discussed, being very impressed at the same time as well as appalled. All right. So if both the trees are null, then guess what? They're the same because they're both null. So I'll return true. Okay. So what other easy cases do I have? Well, easy case number 2 is if I've got something over here, right? But not something over here, right? I have a node over here, but this is not. But If I've got a node over here, but this guy is empty, then great, they're not equal, and vice versa. So that's two more cases right there. So if tree A is not equal to null, doesn't matter which order, and tree B is null, and you're more than welcome to truncate it by like over here, but say same but flipped, right? You know, right? You're more than welcome to do that on an exam, just to say same answer, same condition but flipped, right? Return false, right? If we have something on one side but nothing on the other, then congratulations, that's super easy. Same over here. If tree, because I have this handy dandy copy paste function. You don't on pencil and paper, unfortunately. So there we go. All right. Now we're wandering into our condition where basically it's possible that we have something like this. Okay. So let's just go ahead and put this into an else, just because else we have something for both tree A and tree B. So that means fine, we actually have to do some work. Okay. So not only do we care about them having the same structure, but we also care about them having the same contents. So the first thing we have to do, let's check if the contents of A and B are the same. Okay? So if tree A dot item dot equals tree B dot item, right? If their items are equal, if you did tree A dot equals tree B, whatever, but it's the items that we care about. Tree A dot item dot equals tree B dot item, or rather, if that's not true, return false, right? If those two I'm saying if we've got a 7 over here and a 13 over here, then obviously they're not equal because we care about the contents. And the contents don't equal, so return false. Okay, otherwise, it's getting hard now to think about, so that means it's a good time to go and rely on recursion. Well, we know that basically we have a node here and here, okay? Which means that basically what we have to do, and we also know that the contents in node A and node B are the same, which now means that we need to figure out, that means that these two things are equal if and only if our left subtrees are equal and our right subtrees are equal. Right? Make sense? So let's go ahead and ask that. So I need to ask if my entire left subtree is equal. So I'll say left. So I'll say Boolean left is equal to equals tree A dot left, comma tree B dot left. Boolean right equals tree A dot right, tree B dot right. Okay, and so we figure out, are my left side equals my right side equal to each other, and return left ANDed with right. So this one was a bit of a longer one, but that's what makes it good practice. Notice that it was worth 0 points, so it wouldn't actually be on the exam. You'll have I think you'll have a grand total of I can't remember if it's 2 or 3 tree questions. I think it's just 2 tree questions. And then 1 hash table. Really, it's 1 tree question, but actually I broke it up into 2 methods for you. So, all right. Yes.
Will you post this video tonight?
Yes, I will. I need to, and if I don't, email me frantically, and I'll immediately upload it. Okay, because I gotta upload this. I gotta remember to upload this once I get into my office. So let's see.
So are we looking at like 3 coding questions total?
Yeah, I'll double check in just a second. So, all right. So, and then it's going to be something like this, which we've already done. Write a method that returns what characters in a curse string and how many times. We've done this before, right? In class?
Yeah.
We did? People need me to go over it again? Okay. Let me go over the analysis then, and then I'll tackle this problem 20 afterwards. Okay. Okay. 7. The analysis. What are collisions in hash tables? Why do they occur, and how are they handled? Okay, what is a collision? Yes.
When multiple strings can point to the same key, multiple values can point to the same key.
Yeah, when you just got a vocabulary issue there, which is when multiple keys go to the same index.
Right.
When multiple keys go to the same index. So why does that happen? So yes.
You don't have enough extra space in your storage.
Yeah, because there's more keys. There's an infinite many keys, and a not infinite amount of indices that are available. So collisions will happen as we try to store more and more items. So how do we resolve a collision? Yes.
Go to the right next slot.
Yeah, you can go to the next slot available, which is, does anybody remember what that strategy is called? Where we go to the next available slot. If my spot is taken, I go to the next available one. That is open addressing using linear probing. Open addressing, meaning that basically the address I'm maintaining is open. So if I can't get my spot, I'm going to go ahead and look for the next one. This is contrasted with something called quadratic probing, where with linear probing, I say, okay, if I can't go to my spot, I'm going to look at my 1 to the right, then 2 to the right, then 3 to the right from my spot, then 4 to the right from my spot, and so on and so forth. Quadratic probing says, oh, if I can't have my spot, I'm going to look 1 squared to the right of my spot, then 2 squared to the right of my spot, then 3 squared, which ends up making more gaps, but takes a bit longer to calculate because you've got a multiplication operation in there, too. Okay. The other way you can handle collisions is by that we learned about, because there's a lot of different ways. There's, for instance, cuckoo hashing, which we didn't talk about in class at all, and I don't particularly understand the full dynamics of it, but I know enough about it to summarize, which is rather than you looking for a spot, you act like a cuckoo and kick the other person out of your spot, and then force them to look for a spot. So, so that's so how do they? So the other way we actually learned was chaining, where basically each spot isn't actually a spot; it's a linked list, right? And so if your spot is taken, you just add yourself to the end of that linked list. Ends up being really easy to resolve, but you end up, having the extra overhead of a linked list.
Is that the same as buckets, or is that something?
Buckets. That is exactly what buckets are. The buckets are just linked lists.
So making that particular parking space, or whatever your analogy is, a linked list.
Yeah. So basically, we imagine that okay, I'm going to just, it's more of a column there rather than it's more of a parking column than a parking spot, and I can just pull in behind him. And so long as things are evenly distributed, right, no particular linked list is going to get particularly long. And eventually, once you reach a certain capacity, you'll start spreading them out again, right? So what is the worst case runtime for insertion and deletion algorithms in a binary search tree, and why? So what are the worst case? So average case for adding and removing items from a binary search tree is what?
Log n.
Log n. What is the worst case scenario? N. For self-balancing binary search tree, we'd be looking at log n as well, but these are not self-balancing. Worst case scenario is n. So why? Yeah, if you're unlucky, you get a linked list, or you're just zigging and zagging right and left, right? And you're ever really cutting out half of the items. You're never really reducing your search space by half, right? That's what O of log base 2 of n means. I'd be reducing my search space by half, right? If I had, for some reason, like 4 children, right? And then basically I had 4 branches equally equally divided, right? If I went left or right, I'd be reducing my search space by 3/4 each time, right? Because I'd be reducing down to 1/4, right? All right. So last question is this one, this practice question. Write a method that, given an array of integers, categorizes them into numbers divisible by 2, 3, and 5. So I'm just going to go ahead so that I can get this onto the answer stream as well. And I'm going to make sure that my exam is, I'm going to go through the exam, and I might remove some questions just to make it a bit shorter. So, because I'd rather you have enough time for these. So map integer list split numbers by factors. Okay. And map. All right, so basically we want to split this thing up into a map and categorize each of these integers by certain numbers. Okay, hash map. And what was it, 3 5s and 7s, right? 2 3 5s. Okay. So what we do here is that since we already know the categories, we're going to go ahead and create them. Map.add, map.put, right? It's put, not add. Map.put, I'm going to create a list for all the numbers that are 2s. New array list. Okay, I'm going to create a list for all the numbers that are 3s. And then I'm going to create a one that for all the numbers that are 5s, right? It's the same code. I just made 3 new lists, one for 2s, one for 3s, and one for 5s. Okay. At the end of this, to stop this from having an error, I'll return the map. And now this is fairly straightforward. For int I in array, if I mod 2 equals 0, if the number is a multiple of 2, then I add it to the 2 list, which I get by saying map.get the 2s and .add it, which is pretty nice that I can do that all in one line. It looks ugly, but I mean, what are you going to do? If it's divisible by 3, I get the 3 list and add it to the numbers that are divisible by 3. And if it's divisible by 5, I add it to the 5 list. Right? And these are not mutually exclusive, like a FizzBuzz problem. And that will split it into 3 lists of 3, 5, of numbers that are divisible by 2, 3, and 5. All right. So, and sorry if you sent me an email over the weekend. I was busy enjoying my birthday, so you know.
Happy birthday.
Woohoo! Yeah, yeah. I So yeah, I got my birthday presents early, so because it didn't make sense to wait for them. But my wife got me a new video game that we've been playing together. So yeah,
You got
Super Mario Odyssey.